So this is Unit 3, Lesson 1 of our Pre-Calc 12 class. The unit is called Exponential and Logarithmic Functions. Lesson 1 is called Graphing Exponential Functions. What we're going to learn in this video is how to understand exponential relationships. What does the graph of an exponential function look like, and how to tell if an exponential function is a growth function or a decay function. So first, I want to share a story behind the picture for this unit. So the story goes, there was a man who invented a game on an 8x8 board, like a checkerboard, but it was different because the pieces were different. And basically, the man invented what we call chess. And it became really popular, and it became so popular that the king of the country invited the man to come to his throne room and share the game with him. And the king loved it so much, he offered the man a reward for making this game and making the kingdom so happy. And the reward was, name your price. So the man who invented the game, being a strong math person, asked the king for 1 grain of rice for the first square on the chessboard, 2 grains of rice for the second square, 4 grains of rice for the third square, 8 grains of rice for the fourth square, and so on for each square of the board. It's an 8x8 board, so there's 64 squares. The king, a little confused, but approved the man's request. He did not understand exponential growth, so he did not realize how much grain of rice this man just asked for. So if you have a calculator handy, you can do 2 to the power of 64, and I'm actually going to do that right now on my cell phone, because I don't know the exact answer myself. 2 to the power of 64 is a very big 20-digit number. So the 20 digits, so we're talking way beyond trillions, which is crazy. If you double a grain of rice 64 times, it becomes impossibly huge. So even after the king found every grain of rice in the entire country and gave it to the man, he still owed the man beyond billions of grains of rice. All right, so if you were in class when we started this unit, we played a little game of American Eagle. And the way the game works is everyone lines up on the wall, and we have one person in the middle of the gym floor. They're the eagle. And then they run across the gym, and whoever the eagle tags becomes an eagle for the next round. And so we play 2 games, and we can see the growth of the eagle population for each of the green line curves. So for the first game, we had or at least for one of the games, I'm not sure which was the first, we had 1 eagle in round 1 and 1 eagle still in round 2, and then 2 eagles, and then it growed and it growed and it growed. The other game, we had 1 eagle in round 1 and then 2 eagles in round 2 because that person touched someone the first round or tagged someone, and then it grew from there. And so the eagle population growth here is an example of exponential growth. 2 other examples of growth functions we have is paper folding. So if you take a piece of printer paper, which is approximately 0.2 millimeters thick, and you fold it in half 41 times, it'll be about 140,000 kilometers. So if you calculated that, you would take your calculator and you type in 0.2 and you multiply it by 2 to the power of 41, and you'll get a really big number, around 140 to 143,000 kilometers. If you want to visualize how long that is, it's about the distance from the surface of the Earth to the surface of the Moon, which is huge. It's way bigger than you think it would be, folding a piece of paper in half 41 times. Another example of exponential growth would be the interest due on a credit card. So a credit card might have 20% interest if you're late for a monthly payment, and if you miss a due date, then they charge you 20% of whatever you owe them. If you miss a second month's due date, they charge you 20% on top of what you currently owe them, which was the previous loan amount plus the previous interest fee. And so each month you owe more money, but the amount of money you owe each month is increasing. And it's increasing, well, by 20% to a power of x, and x being the number of loan months you've missed. And so credit cards can be very dangerous in that because of the exponential growth of the debt, or what it could become. So now another example of exponential functions is exponential decay. So when something decreases in value, in my hometown, there's a nuclear power plant, and the nuclear waste, they say, has a half-life. And by half-life, they mean that the nuclear waste that they store over time gives off radiation, and a half-life would be the amount of time before it loses half of its radiation or radioactivity or whatever the word is. And it's a ridiculously high number, like, I don't know, 10,000 year half-life. Also, my first car was a 1989 Ford Tempo. Yeah, not a lot I could say about that car. However, it was a good first experience. Everyone should have a crappy car for their first car because it builds character. Anyways, if you buy a brand new car, or any car, you may have heard somebody say that cars depreciate in value. And what that means is the value of the car goes down as it gets older. Now, collectors' vehicles and special editions usually are the exception. If it's a collector's item, its value might go up just like any other collector's item. But in general, cars lose value over time, and that the amount of value it loses decreases over time, or it decreases in value at a decreasing rate, you could say. So if I were to say a word for exponential growth and decay, I would say that exponential growth, something is increasing at an increasing rate. And if I'm talking about exponential decay, something is decreasing at a decreasing rate. Okay, so how do you graph this thing? And what kind of things can we get from this graph? If we were to graph a function f, which is defined as f of x equals 2x, or 2 to the power of x, we would get the red curve on the graph. And so what I would do is I would just plug in values for x. If I plugged in 0, it would be 2 to the power of 0. Well, anything to the power of 0 is 1. If I plug in 1, then I get 2 to the power of 1, which is 2. And then 2 would give me 4. 3 would give me 8. If I go negative exponents, negative means that we are dividing by 2 instead of multiplying. So 2 to the power of negative 1 would be the same thing as 1 over 2. And 2 to the power of negative 2 would be 1 over 2 positive, or 1 over 2 squared, which would be 1 over 4. So if I graph this thing, if I start at x equals 0 and I go to the right, we're doubling each time the previous numbers. So we go up 1, and then we go up 2, and then we go up 4. If I go left, I'm doing the opposite of doubling. I'm halving each time. So half of 1 is 1/2. Half of 1/2 is 1/4. And if I kept going half the distance between our line and the x-axis, half of 1/4 would be 1/8, 1/16, 1/32, 1/64, 1/28. And we'd be getting infinitely closer to 0, but we would never equal 0. I'll say it again, we will get infinitely close to 0, but we will never equal 0. Because if you take half of something, you still have something left over. Half of something is never nothing, in other words. So what we find is we have a graph that goes to the left that approaches 0 but never actually reaches 0. And what we call this is a horizontal asymptote. A horizontal asymptote at the line y equals 0 is that an asymptote is a line that our curve approaches but never touches. All right, if we're looking at the domain of this function, because I can plug in any value for x I want into the exponent, then we say our domain is all real numbers. The range of our function, the y values we get, and well, because of the asymptote, we know we can't get 0, and we can only get above 0. So we say our range is from 0 to infinity, and we use normal brackets because it does not include the point 0. We could also write it as an inequality. Y is strictly greater than 0. Another example, so if the last example we are growing by a factor of 2, we have an example of exponential growth. This one we're halving each time we move forward. So this would be an example of decay. And if you notice, it is related to the last graph. If I flip the last graph over the y-axis, we pretty much get the same graph. Because instead of multiplying by 2 to the right and dividing by 2 to the left, we are now dividing by 2 to the right and multiplying by 2 to the left. And so if we look at our graph, we can see when x equals 0, we get the same value of 1. But now if x equals 1, then we have 1/2, and we're going half to the right. We still have a horizontal asymptote at y equals 0. Our domain is still all real numbers because we can still put in any value of x for the exponent. And our range is still 0 to infinity, not including 0. All right, so if I were to graph one of these things, what I want to do is I want to figure out a couple things. I want to know the horizontal asymptote. I want to know if I plug in x, what is 2 to the power of x equals, and then just subtract 3. And so if we just throw in random x values, then we'll get some fraction answers. So if we kind of understand the behavior of this graph, we can work our way around the fractions. If we really don't like fractions, we can avoid them. And we can lean on our understanding of exponential. So I know what the graph to the right would look like. It looks like 2 to the power of x. We have 2 to the power of 0, 2 to the power of 1, 2 to the power of 3, 2 to the power of 4. And then just subtract 3 from that, and we stick with whole numbers. That's fine. And then I can kind of see where my graph looks like on the right. So 0 goes to -2, 1 goes to a -1, 2 goes to 1, 3 goes to 5, and I can get the right side of the curve. And now the left side of the curve, I know, since when I go left, I'm instead of multiplying by 2, I'm dividing by 2 every time. So I'm just going to cut the distance in half each x value I go to the left. Notice we have a horizontal asymptote at x or y equals -3, which is consistent with the fact that our function has a -3 attached to it. When we slap a -3 or a plus number at the end, that will affect the vertical translation. And so in this case, a vertical translation for an exponential function means we're going to move where the horizontal asymptote is. Okay, here's another example. So again, we have +1 attached to our decay function. And so our horizontal asymptote is going to go up 1 unit. So instead of y equals 0, it's y equals 1. Otherwise, it's the exact same graph as 1/2 to the power of x. That changes our domain. Our domain goes up from 1 to infinity. The last graph, our domain would have been -3 to infinity. Sorry, our range would be -3 to infinity. Our domain is all real numbers. Our domain for exponential functions is always going to be all real numbers. So we have a basic understanding of exponential functions. We've kind of seen a little bit how to graph these things, and hopefully we can look at different exponential functions and determine if it's growth or decay.